Hi, I'm Paul Methfessel from the Hasso-Plattner Institute in Germany, Potsdam. I'll present you MµSE, an editor for supporting exploration of software-hardware interactions through examples. Embedded systems consist of a microcontroller unit as part of an electrical or mechanical system. It interacts with the physical environment through peripheral devices and is often programmed through another computer. Writing code for these devices often requires gaining knowledge through prototyping to learn how to use the devices properly for the task at hand. Additional difficulty is added to the prototyping process through points of failures that can not only occur in software, but also in hardware, the need for real-time interaction, and both efficient and generalized devices. To better understand how developers prototype embedded software, we conducted a formative study. We asked embedded programmers to describe their process when exploring and building a simple robotic system. We found that developers work on isolated software components that mirror the used hardware components and explore their assumptions using concrete examples with a fixed environment and inputs. For example, they asked themselves what the threshold for detecting the line on the table might be. To answer, they explore a light sensor through an example where they move it over a line and observe the resulting values. Participants described working in a bottom-up fashion. They first complete individual components for hardware devices and subtasks. They then move to higher abstraction layers until the whole application is composed. When errors occur, participants also use examples to debug code, because examples provide a mental model of expected behavior that can be compared to the actual behavior. A downside of the developer's approach is that these examples are built using temporary code that needs to be commented out or removed to switch to another component or the full application. Print statements, which are used to observe internal state, are also only temporary and clutter the implementation code. Furthermore, the time it takes to compile and upload code to the MCU and then to recreate a physical setup to an example is a break in attention. We conclude from the formative study that the friction of managing and recreating ad hoc examples in code discourages a structured and well-isolated exploration of errors across hardware and software layers. To remove this friction, we introduce MµSE, which makes examples and the means to observe them independent from the implementation. In MµSE, examples are attached to components in a separate window and can be added and switched with a single click, which removes the need to change the implementation to switch examples. Examples are executed live when code is changed, and automatically placed probes show live values, removing the need to write print statements. Examples can also replace a component's dependencies to enable isolated exploration. Examples, replacements, and probes are implemented in the editor by code rewriting before the compile step. For platform independence and liveness, we execute the code on the developer machine and only transfer I/O calls to the MCU, like analog read and digital write. Since no new code needs to be uploaded to the MCU between code reloading, the time to execute is improved, while the remote procedure architecture we are using introduces a performance overhead with each I/O operation, which we further discuss in our paper. To evaluate MµSE, we conducted an exploratory user study where participants had to program their own embedded system. Our first research question is, how and when do developers address gaps and mismatches in their mental model while using MµSE? To evaluate this research question, we gave participants a robotic car and the following task. The car should first drive forward until its light sensor detects a line, then stop and wait for a button to be pressed, which triggers it to drive back to its initial position, which is stored using its motor encoders. To answer the research question, we observed how participants dealt with questions, which we call known unknowns, and unexpected behavior, which we call unknown unknowns. This table shows which tools they use in both cases. Based on our observation, we grouped insights by whether it concerns input or output. Input would, for instance, be reading from a light sensor, and output would be driving the motor. Known unknowns and unknown unknowns for input were mostly answered using probes. Developers actively wrote code that was easily observable by probes, and automatically praised probes would show unexpected values even when the developer was not actively testing. Known unknowns for output were tested through executing code and observing it in the physical environment. This process was sped up through live reload. However, we noticed that MµSE lacks support for detecting unknown unknowns in output. In such cases, developers would notice an erroneous behavior, but could not detect which component was its origin. To understand potential differences in the behavior of non-expert and expert developers, we also performed the study with 2 experts. For most of the user study, the experts showed the same assumptions as our first group. Both agreed that having a real-time visualization of runtime values is helpful for their work, as most of their mistakes in their daily work come from small typing errors in complicated algorithms or simple wrong assumptions that will normally be overlooked. The experts also stressed the importance of being able to adapt the tool for many different setups and the need for low latency, especially in real-time applications. Now that we have a clear picture of how MµSE is used in practice, we can discuss some additional observations we have made during the study. When designing MµSE, we tried to keep changes to the Arduino RPE and C++ syntax to a minimum, as to not confuse developers already familiar with Arduino RPE and embedded programming. However, this generalized approach requires developers to write examples and replacements in such a way to make a device testable, while a tool with knowledge over common hardware devices might automate such a task. Future work could further improve on MµSE by adding additional probes that not only visualize expression values, but also make the control flow visible, like showing which methods and statements are executed. The lack of this information sometimes added confusion in our study. A major limitation of our solution is that it stops at the system boundary of the MCU. The physical state of the robotic car is not managed by MµSE and may thus break the developer's fast feedback loop. Future work could consider dedicated research instructions that would, for example, drive the car back to a reset position, or show prompts to the developer to manually reset the car to a well-defined setup, improving repeatability. We have now seen how, rather than resorting to commenting out code and print statements, MµSE offers first-class examples and automatic probes. In our exploratory user study, we found that the participants' workflow was well supported by MµSE, and especially automatic probes were praised. We also noticed some areas where more work is needed, for instance for inspecting and managing the physical state of the hardware. Through 2 expert interviews, we found that MµSE concepts would be appreciated in a professional setting. In conclusion, we believe MµSE shows how a workflow for embedded software could be realized that supports embedded programmers to perform faster, more effective prototyping. For more information, please refer to our paper, and thank you for listening.